Everybody. So the topic of today's video is going to be about modeling robotic systems in the state space description. Okay. So we're going to discuss a little bit about the state space description and what do we mean by a state space model. How do we transition from a set of differential equations to the state space description? And then we're going to close by discussing about what we're about to do in case of nonlinearity in the system. So let's begin with the basics. Okay, let's go back around 100 years to, the development of classic control theory. Now, in classic control, you may have had it in an undergraduate uh, course. The idea is to start from a differential equation of nth order. And when I say order, I mean the highest derivative present in the system. So let's say this differential equation describes some sort of behavior, like let's say a mechanical system, for example. Okay. And the idea in classic control is to take the Laplace transform, okay, and transform the system from a differential equation into a rational polynomial function, okay, which is called the transfer function, okay. So the transfer function is a great idea, extremely valuable tool because it allows us to go and have a direct input-output relation between the input, which is, as you see, the variable u right here, and the output, which is some sort of available measurement, usually the direct variable x that we have here. It is very easy to solve, so you may not be extremely familiar with differential equations, but using Laplace transform and transfer function, it is very easy to solve the system. And not only that, you can actually analyze the behavior of the system, like how fast does it move, if it goes to infinity, if it goes to zero, if it performs an oscillation or not. You can do all of that, all of this analysis without solving the actual system, right? And also you can define control designs, control techniques using the transfer function. Okay, so the idea is to get rid of the differential equation and just use the transfer function of the system. Now, this in the classic control, but if we jump into the 60s, there was a very good, a great researcher called Rudolf Kalman who offered a different approach. So the idea of Kalman was this. Okay, everybody, we have an nth order differential equation. What if instead of this differential equation, which is of high order, we got n differential equations, so the same in number as this value right here, but all of them of first order. Okay, and the good thing is that by having this description of n differential equations of first order, I can write all of them in a matrix form. This is very easy to do. I'm going to show it later. And this way, I'm going to get this sort of description that you see right here, where U is the input to the system, X bold is the state vector, so we may have more than one states, which is actually the case. Y is the output, and by output, we usually mean some measurable variable here. Okay, so if parts of the state are measurable, these are actually the output of the system, right? And A, B, C, and D are matrices. So this difference in going from nth order to n differential equations of first order has many pros. Okay, because the obvious question is this. Okay, Lazarus, I mean, why the hell are we going from just one differential equation to multiple differential equations? Okay, upon first looking at that, it makes no sense. Like it makes you think that no way this is a better choice. But actually, it is a better choice because now you can have an input, output, and state. So input, state, output, I should say more correctly, relation. The idea is that again, pretty much like the transfer function, the system is very easy to solve, but also it offers one great pro here. You can do the system analysis by studying the matrices. So you can do an analysis about the system behavior, like does it go to infinity, does it oscillate, how fast, how slow does it oscillate, what's the steady state, what's the settling time, and so on, simply by studying the matrix A, right? You can perform control by simply studying the relation between matrix A and B. And also you can do what is called the observability analysis, which means if I am able to estimate what happens internally in the system, again, by looking only at the matrices A and C. And also, in contrast to the case of the transfer function, it offers a way to transition between linear and non-linear cases. This does not appear in transfer functions, so this is a great pro for this description. Now, we have, by adding this form of description for our system, we have a triad of different descriptions, which are actually equivalent. We have ODEs, differential equations, we have the transfer function, and we have the state space description. And the good thing is that these descriptions are equivalent, so you can go back and forth from one to the other. And of course, this raises the question, which is better? Of course, everybody will tell you there is no such thing. It's very hard to actually make a decision on that. I would say it's much more common though nowadays to use state space description. But of course, this is a trick question. There is no better description for me. I mean, no, if you ask me, I think state space is better. But again, you can do a great analysis using any of these three descriptions for a system. Now, this is the state space, okay? So from instead of having one differential equation, we have many. So as you see right here, U1, U2, and so on are the inputs. X1, X2, X3 up to Xn are the states of the system. And we also have some outputs, Y1, Y2, Y3 up to Yp. Remember, the outputs don't have derivatives, right? That's why they're the outputs. So they are simply a linear combination of the state and input. And I can take the above system that you see right here and simply write it in a matrix form. So how did I go from this description to the description here? Simple linear algebra. Okay, I didn't do anything in particular that is special. I simply took all of these terms that I have colored actually to make them visually clear, and I have written them in matrix form. And in this way, I can define the state vector, which is actually the set of all the states, the input vector, which is the set of all inputs, the output vector, which is y1 up to yp, and then the appropriate matrices A, B, C, and D, right? So this is the idea, to somehow find a way to obtain this description, because afterwards, we can do all our analysis using A, B, C, and D matrices, right? So how do we do that? The idea is very simple. So it is very standardized. You can do it again and again, no matter what the system is. Okay. So let's say we start from this differential equation. U is the input, X is the state of the system, the variable of the system. So in order to go into a state space description, we need to define n different states. I know that because the differential equation is of nth order. So first clue, you see differential equation of nth order, you need n states. That's granted, okay? And of course, I need n differential equations. So the way that I do that is very simple, okay? So I start and I set my main variable of interest, x, as my first state. So x1 is x, right? The second state, x2, is the derivative of x. Okay, so this becomes x1 and this becomes x2. Okay, of course they are interrelated, right? Because since x2 is the derivative of x, is also the derivative of x1, right? This makes sense because x equals x1, so x dot is x1 dot. Then x3 is the second derivative of x, right? Which means, of course, that it is also the derivative of x2, right? X4 is the third derivative, which is the derivative of x3, and so on. So as you see right here, x becomes x1, this becomes x2, and so on and so on, until this term becomes xn. Okay, as you see right here, xn, which is also the derivative of xn minus 1 term. Okay, so I have defined all of these terms as individual variables, and I have these differential equations because that's my first differential equation, That's my second, and that's my second to last differential equation, right? So the only term that is not defined is this one, xn, the highest order term. But do I need an extra state for this one? No, because simply put, this term right here is actually the derivative of the previous term. So this term, x to the nth, becomes the derivative of the nth state. Okay, so replacing all of these into this first differential equation, I obtain this formula. So alpha 0 x becomes alpha 0 x1, and so on and so on. And x differentiated to the nth degree becomes x nth state derived in the differentiated. Okay. So only thing I have to do now is simply write them in matrix form, because these are my differential equations, the first, the second, and the nth, right? So I only have to rewrite them using simply linear algebra. So this is the end result. Okay. From this differential equation, I went into this state space description. And this is very standardized because actually we have ones in the upper diagonal, everything else here is 0. And the last line includes the terms that appear in the differential equation. So for x1 here we have minus alpha 0, then we have minus alpha 1, and so on until minus alpha to the n minus 1. Okay, and in the same way we have the input matrix B. So this is the state equation for the state space model. And now I only have to decide what is going to be my output. And for the output, the things are simple. Since this is the state, let's assume that what I want to read, what I want to measure in the output is actually the first state, because remember the first state is actually the variable that I'm studying, the x variable, right? So then I simply use linear algebra, and I have one line multiplied by one vector. I only want the first element, x1, so I put zeros everywhere and 1 in the first position. So again, this is very, very simple linear algebra. If you don't understand this, you simply need to brush up your basic linear algebra skills, right? So the derivation is very, very, very easy. And you can do this with any type of system. So for that matter, what I'm gonna do now is give you some examples about some basic mechanical systems. So let's go. This is our first example, super classic. I mean, if you open up any book on automatic control, you will see the spring, mass, and damper system. Okay. Now, let's write this system in state space. First of all, we need the differential equation, and to derive the differential equation, we need some basic understanding of Newton's law. So the sum of the forces applied to a body is equal to the mass times acceleration. Okay, so we have this equation right here, m times the acceleration of the system, of the mass, I'm sorry, is equal to the forces applied. And when the system is moving this way, the forces applied are the input, which is positive, and then the spring drives the system, draws it backwards, and the damper as well draws the system backwards. So that's why we have these two negative terms. Kappa, which is the spring coefficient, and C, which is the damper coefficient, which applies, of course, force which is relevant to the derivative of the, I'm sorry, to the acceleration. Okay, so we use these two terms on the left, and we end up with this differential equation. It includes u, the displacement, the acceleration, the velocity, I'm sorry, and the acceleration, right? So let's derive the state space of the system. Okay, what do we need? Since the system is a second order differential equation, okay, we need two states. And I'm going to define the states the same way as before. Okay, so the first state is Q, which is the displacement. And the second state, I have a typo here, it's not acceleration, my apologies, is the velocity. So the second state is the velocity of the mass. Okay, and then we have this third term right here, but as I told you, we don't need an additional state for this term because this q double dot term is actually the derivative of the second state. Okay, because the acceleration is the derivative of the velocity. So we write down these differential equations. This is the first one, x1 dot equals x2. And the second differential equation is this one. U remains the same. Q becomes x1, Q dot becomes x2, and Q double dot becomes x2 dot. Okay. So I only need to write these two differential equations in matrix form. Again, this is what I do here. So these are the two differential equations, and these are the same differential equations written in matrix form. So it is very straightforward to derive the state space. Okay. Of course, I'm not finished. I need to define an output as well. So this depends on what I'm going to measure. Now, assuming that I can in some way measure assuming that in some way I can measure uh, my displacement, this means that this output is just the displacement. If I do linear algebra multiplication here, I get x1. But if I assume that I can also measure the velocity, then I have this identity matrix where the first output is the displacement, the second output is the velocity, right? So simple as that for deriving the state space equation of the system, okay? And remember, we need both the state equations and the output equations to have a full description of the system. Now let's consider a second example, which is from robotics. Let's say we have a system that you see right here. We're actually looking at it from above. So we're looking down below and we have three links and there are prismatic joints. And prismatic joints means that they can only move in a fixed direction. So forward and backward. Okay. So we can derive the state space for this system, but I'm not going to write this down. So let's assume that we already have the state space description. And the state variable is this. As you can understand, for each body, we actually have two states, just like before. One is the displacement, and the second is the velocity. So here we again have, since we have three bodies, okay, three links, we have six states. So we have the displacement of the first link, the derivative of the displacement, okay, the velocity. For the second link, we have the displacement of the link, the velocity of the link, and then for the third link, we have the displacement of the third link and the velocity of the third link. So overall, six states. So I'm asking a very simple question. Considering that this is the state space and the state equation, the state variable, I'm sorry, what is the displacement of the end effector? The end effector is the black thing that you see right here, the grappling hook. Okay, with respect to the axis x0 and z0, which is the initial point right here. Okay, so they are horizontal, then the vertical displacement, right? And this is very easy to understand. Okay, since we have displacement in two coordinates, I'm actually gonna have two outputs, right? So the first output, let's think about the horizontal position of this end effector. This goes up and down, this goes left and right, and this goes up and down, right? So the displacement in the horizontal vector for the, in the horizontal plane for the end effector is actually just Q2. So one output is going to be Q2, the displacement in the horizontal axis. Now in the vertical axis, the position here is going to depend on how high is Q1 and how high is Q3. So the displacement overall is going to be the addition of these two, Q1 plus Q3. Okay, so let's write this down. This is the output equation. Okay, the first output is, if we do the multiplication, is Q2. And the second output, if we do the multiplication, is x1 plus x3, which is the fifth state, right? So simple as that, by understanding the vector of the state space, we can understand which is going to be the output. Okay, so in this situation, the output is a linear combination of all the states. So you don't need like extreme mathematics to understand it. You just need to understand what is the vector and then perform some basic linear algebra based on what the output is going to be. Now let's go and consider one more example. Again, this is a bit more simple. We have two links and two prismatic joints. I'm sorry, two joints and two prismatic links. So we can only move up and down right here and up and down, left and right on this direction, right? So the equations of motion, I mean, are not that easy to derive. We need a thing called the Euler-Lagrange equations, very basic in most robotic books. So there is a procedure to derive the equations of motion. I'm not going to show the procedure here because it is a course just by itself. But let's say we have actually done this procedure and now we get the differential equations. Remember, we have two masses here, okay, two different joints. So pretty much what this means is that we are going to have a differential equation for the motion of each joint individually. And this is what we get. So uh, these are the two differential equations. F1 and F2 are the forces applied by the motors on the joints that move them forward and backward. And J is the gravity effect. Okay. So how can we understand how many states do we want? Okay, and how big is going to be is the state space going to be? So for the first mass, for the first link, okay, again, since we have a second order differential equation, we need two states. So the first state x1 is the displacement q1, and the second state is the velocity, which is x2 equals q1 dot. Okay. And the same thing holds for the second link. Okay, so the third state is going to be the displacement q2, and the fourth state, the derivative of the displacement, okay, the velocity q2 dot. Okay, and again, these two higher order terms are defined in terms of q2 dot and q4 dot. So if I replace everything and I write them down in this way, I have four differential equations of first order. And this is the state space, Q1, Q1 dot, Q2, Q2 dot, right? And I can simply write them in matrix form, which gives me a great formulation. A, B matrices, and this is an additional term. You can consider it, for example, like an additional noise or an additional disturbance into the system, which is very common in state space description. And for the output, again, we need to understand that this is the end effector, and we are measuring practically the displacement in the horizontal and vertical axis, which is basically Q1 and Q2. And that's why we have two outputs. The first is Q1 and the second is Q2. So again, simple as that. Once you understand what is the state space, you can derive the output very easily, right? So we saw a couple of examples. Two of them are robotic examples, and one was a spring mass damper example. All of them linear. So a big question arises. Are we always gonna be that, you know, lucky? No, you're not gonna end up with a linear system in any case. Actually, in most cases, the system is going to be non-linear. And in this case, things are not that simple, especially with respect to control. So this is a much more general formulation of equations of motion. Or if you want to write them in state space form, we have this alpha times x, beta times u, which is classical state space. But let's say we also have this f function, which is generally a nonlinear function of the state. Okay, so one might say, okay, now that the system is nonlinear, every technique that I know on state space is useless. This is not the case, actually. State space techniques are still very useful for nonlinear systems. First of all, there is a very nice transition between linear and non-linear control. We are not going to show that. But also there is a very nice technique to go from a non-linear system to a linear system in very special situations. And I'm going to explain that with an example. So this is a classic example. Some people call it inverted pendulum. Practically, it is a single link. It has a DC motor and it has a rotational motion. Okay. So either you call it rotational link or they simply called pendulum, doesn't matter. Okay. So the differential equation that describes the motion of this system is nonlinear because the displacement now is measured in radians. So there are, sinusoidal terms involved here. So the state space has some linear terms, but actually it has this sort of sinusoidal term. So it's a nonlinear system. But what happens here? In situation, we can have the opportunity to pretty much obtain a simplified version of this system under a specific condition. To understand it, let's zoom in. Okay, let's go and zoom in here to the case where the angle of displacement is very, very small. So let's say we are vertically right here, and the displacement is very, very close to zero angles, right? To 0 degrees. What happens there? If you actually see the plot of the sinusoidal function right here, and I have also plotted the bisector, you will see that for very, very small angles around here, the sine function and the bisector are almost identical, right? Uh, Especially if you go into this region, you see that the bisector and sine are almost the same, right? So this very simple reasoning tells us that if the angle of rotation is very, very small, you can write simply, instead of sine of x1, simply write x1. And this is a very clear and classic simplification, okay? It's called linearization as a process. And by performing this simplification, the nonlinear term gets lost. It is replaced by a linear term. And now we can transition from a nonlinear system to a linear system. Okay. So this is a very nice way of simplifying the dynamics of the system. Of course, this doesn't hold everywhere. As I said, we need to be on specific angles, very close to zero. But believe me, this is a very valuable technique because we can apply it to simplify the dynamics of the system and then consider some control technique that will be much, much more easy to apply and much less energy consuming. Okay, so this is a very classic technique. It can be actually generalized and written in a more mathematical formula, but this simple geometrical reasoning behind it makes absolutely sense in this case. Okay. So you can linearize a nonlinear system as long as you are very close to the equilibrium. Okay. Equilibrium is this part right here where the pendulum remains completely still, right? So this is an equilibrium, and close to the equilibrium, we can linearize our model. Okay. So I'm going to leave you with two additional questions. First of all, I need you to think how many equilibria does this system have? We already discussed about this one, okay, where the angle is right here, zero. But actually, there are more equilibria. Actually, there are infinite equilibria. But as a first thought, I would say, try and understand what are the two equilibria of the system. Okay, so they may be infinite, but I want you to understand what are the two distinct equilibria of the system. If you understand them, then you can understand the rest. Okay, so this is a very important question because only around this equilibrium we can perform linearization. And the second example, this is a robotic arm, so it actually consists of uh, two links and two rotational joints. So in this case, you can model this as a double inverted pendulum or a double pendulum. And again, I want you to think how many equilibria does this system have? Okay. Again, there are infinite, but let's say initially I want you to understand four distinct equilibria for this system. Okay. It's going to be amazing once you understand that this system doesn't have just one equilibrium, but not only two equilibria, but it actually has four, and we can say infinite equilibria actually. So think of it as an open exercise, right? So the examples here are taken from some very classic books, like the book by Control of Robot Manipulators and the Robot Modeling and Control. These are very, very classic books for teaching control theory. I would advise you take a look at them and also on all of these references. So any questions that you have, you can write them in the description of the video, in the comment section, and I will try and reply to all of you. Okay, so thank you very much.